at 35,000 feet. Here is what is actually happening behind that cowling. How turbine blades survive temperatures beyond their own melting point. Why the British government allowed the jet engine patent to expire. What the FADEC does when a pilot pushes too hard. How ice crystals forming inside the engine nearly caused a disaster. Every second you're in the air, a jet engine swallows roughly 1,000 pounds of air. It compresses that air to temperatures hotter than molten lava. Then it blasts it out the back at speeds approaching 1,000 miles an hour. The whole sequence, from intake to exhaust, takes less than 1/120th of a second. That is what is happening just a few feet from your seat while you read the safety card. At its core, the machine is elegantly simple. Air goes in, it gets squeezed. Fuel is added and lit. The expanding gas shoots out the back. The reaction to that rearward thrust pushes the aircraft forward. Sir Isaac Newton worked that out in 1687. But turning that principle into a machine that can run reliably for tens of thousands of hours at temperatures no metal should survive took another 250 years. The man who cracked that problem was a Royal Air Force cadet named Frank Whittle. In 1928, at just 21, Whittle wrote a thesis arguing that aircraft could fly at very high altitudes using a continuous combustion gas turbine instead of a piston engine. His instructors gave the paper a distinction. The Air Ministry told him the idea was impractical. Whittle filed a patent anyway in 1930, paid for with his own money, about £5. The British government let Whittle's patent lapse in 1935. They declined to pay the £4 renewal fee. In Germany that same year, a physics student named Hans von Ohain reached the same core idea independently. Von Ohain had the backing of the Henkel Aircraft Company. By 1937, both men had working bench engines. The race to fly a jet-powered aircraft had begun, and neither man knew the other existed. Von Ohain flew first. The Henkel lifted off on August 27, 1939, 5 days before Germany invaded Poland. Whittle's engine flew 2 years later in the Gloster E-28/39 in May 1941. By the end of the war, both sides had jet fighters in combat. The technology was out of the experimental stage. Now engineers had to figure out how to make it last and efficient enough to carry passengers. Today, the jet engine is the most thermodynamically efficient heat engine ever mass-produced. A modern high-bypass turbofan converts roughly 55% of the chemical energy in its fuel into useful thrust. A car engine manages about 25%. That gap, 25 versus 55, is why a Boeing 787 can carry 300 people halfway around the world on a fuel load that costs less per seat mile than a bus ticket in 1960. Walk up to a modern turbofan on the ground, and the first thing you see is the fan. On a wide-body aircraft like an Airbus A350 or a Boeing 777, that fan is roughly 11 feet across, about the diameter of a compact car. It spins at up to 3,000 revolutions per minute at full thrust. The tips of the blades are moving at close to the speed of sound. Each blade is a precision airfoil shaped to bite into the air like a wing. That big fan does two things at once. About 80 to 85% of the air it pulls in never enters the core of the engine at all. It bypasses the hot section entirely and accelerates straight out the back as a cold, fast-moving column of air. That bypass flow generates most of the aircraft's thrust. It also dilutes the hot exhaust, reducing noise significantly. A high bypass ratio is why modern jets are quieter than the screaming turbojets of the 1960s. The remaining 15 to 20% of the incoming air goes into the core. This is where the serious thermodynamics happen. The first station inside the core is the low-pressure compressor, a series of rotating discs studded with blades, alternating with fixed stator vanes. Each stage squeezes the air a little tighter and pushes it into the next stage. The pressure rises steadily. Temperature rises with it. After the low-pressure compressor, the air enters the high-pressure compressor. A modern engine like the CFM56, which powers most narrow-body airliners today, has around 25 compressor stages in total. By the time the air reaches the end of the high-pressure compressor, it has been squeezed to about 40 times its original pressure. Its temperature has climbed from the ambient outside air to over 600 degrees Celsius, and combustion has not even started yet. The compressed air then enters the combustion chamber, sometimes called the combustor. This is an annular ring surrounding the engine core lined with small fuel injector nozzles. Jet fuel. A highly refined kerosene called Jet A is sprayed in as a fine mist. The mixture ignites. Temperatures in the combustor reach between 1,700 and 2,000 degrees Celsius. That is hotter than the melting point of the nickel alloys the chamber is made from. So how does a metal combustion chamber survive temperatures above its own melting point? It does not do it passively. The combustor is cooled by a continuous film of air that flows along its inner walls, keeping the metal away from the hottest gases. The chamber is also perforated with thousands of tiny holes that let cool air seep through in a process called effusion cooling. The engineering is so precise that each hole is machined to within fractions of a millimeter. The hot, expanding gases from the combustor rush into the turbine section. This is where energy is extracted from the gas stream. The turbine blades, spinning at up to 15,000 revolutions per minute in the high-pressure stage, are shaped to capture the kinetic energy of the passing gas and convert it into shaft rotation. That rotating shaft drives the compressors at the front of the engine. The turbine is literally powering the machine that feeds it. Turbine blades are among the most technically demanding objects ever manufactured. Each one operates in gas flows hotter than its own melting point. Each one is cast from a single crystal of a nickel superalloy, a process where the metal is grown atom by atom in a controlled solidification furnace to eliminate internal grain boundaries that would cause cracking. And each blade contains an intricate internal labyrinth of cooling channels thinner than a human hair through which cool air is pumped continuously during flight. After the high-pressure turbine, the gases have given up much of their energy, but they are still extremely hot and fast-moving. They flow through the low-pressure turbine, which extracts more energy to drive the large fan at the front of the engine. By the time the gases reach the exhaust nozzle, they have cooled significantly, but they are still moving fast enough to provide the remaining thrust that, combined with the bypass flow, keeps a 600-ton aircraft in the air. All of this, from intake to exhaust, happens in a cylinder roughly 8 feet long and 4 feet in diameter. The entire thermodynamic cycle repeats not once per revolution, but thousands of times per second in the annular combustor. Every rotating component is spinning at a different speed on a different shaft and expanding at a different rate, and all of them are connected by shafts, seals, and bearings that must hold tolerances measured in thousands of an inch, while the whole assembly heats and cools by hundreds of degrees. The materials science behind this is extraordinary. The fan blades on most modern engines are made not from metal, but from carbon fiber composite. Each blade a hollow structure of woven carbon fibers set in an epoxy matrix. They are lighter than aluminum and stronger than steel in the directions that matter. A wide-body engine fan blade weighs about 12 pounds. A bird strike that would shatter a metal blade is absorbed and shed by a composite one, a requirement that every certified engine must survive in testing. Bird strikes are one of the more dramatic tests in the engine certification process. Before any commercial engine can be approved, engineers must fire a 4-pound chicken from a pneumatic cannon into the running engine at takeoff speed. The engine must contain the impact and keep producing at least 75% thrust for another 20 minutes, enough to land the aircraft safely. Engineers also fire a sequence of smaller birds in rapid succession to simulate a flock encounter. The tests are recorded with high-speed cameras. Then there is the ice ingestion test. At altitude, the engine intake can accumulate ice crystals that have formed inside the engine itself, a phenomenon discovered when several engines unexpectedly flamed out over the Indian Ocean in the 1990s. The mechanism was not understood for years. Eventually, researchers found that at certain altitudes, tiny ice crystals bypass the engine ice detection systems, accumulate on warm surfaces inside the core, then shed suddenly and flow into the combustor, suppressing the flame. That discovery prompted a complete revision of engine icing certification standards in 2015. Manufacturers had to retest or redesign. Some engines were modified with ice-shedding heaters. Others required revised pilot procedures. The episode is a useful reminder that even a machine as thoroughly engineered as a jet engine can encounter conditions its designers did not fully anticipate. The envelope of what engineers know keeps getting pushed outward by the edge cases the real world produces. Fuel management is another layer of hidden complexity. A fully fueled Boeing 747 carries about 57,000 gallons of Jet A in tanks distributed across the wings and fuselage. The fuel serves a second purpose beyond combustion. It cools hydraulic fluids and lubricating oil by absorbing heat as it circulates through heat exchangers before reaching the engine.